With us is Professor Balla Rajkumar. He is a professor of chemistry and professor of atmospheric chemistry in the chemistry department since 2006 when he first joined the department. Professor Rajkumar has a background that he is from Andhra Pradesh and did his PhD in the Indian Institute of Science, Bangalore. He was the first to introduce shock tube experiments in IISc Bangalore, shockwave chemical chemistry, chemical kinetics experiments. So his project was a joint project between two departments, the aerospace department and the chemistry department. So he had virtually two guides, and his chemistry professor guide is Professor Arunan, who is the spectroscopy chemical kineticist. He himself was also an expert in shock tube experiments before joining IISc. Professor Rajkumar set up the first shock tube lab. He is very well known in IISc for that. And then he went to Boulder, University of Boulder in Colorado in the United States, Western United States. And he spent with one of the very famous atmospheric chemists, Professor Ravi Shankara, who set up some of the most beautiful atmospheric chemistry experiments and also the experiment called the cavity ring down laser spectroscopy induced fluorescence. So he worked with him for several years, came back here, has been teaching physical chemistry, became a professor within a few years, and has been contributing. I understand last year or year before last year, he had a little more than 24 articles in the Journal of Physical Chemistry.
By now it is
1 year.
21.
21. You know, that's a
peak.
That's a
So far.
that's about half of my total number of papers. Okay.
It's not number of papers.
But he has been working very hard. He set up in IIT Madras he is extremely well known for setting up the first, again, the shock tube laser spectroscopy experimental setup. And unfortunately today we don't have the time, but when you come back or when you want to interact in IIT Madras sometime, you must visit his lab.
So they can visit now also?
Yeah, during the lunchtime if they have, but we have a tight class schedule, so we'll do that another time. But you will show the lab anyway. In the pictures, you will show the lab, some of the labs. So it is my pleasure, and he has been my very close colleague and helpful in many ways, many ways in the department since he joined in 2006. Now it's almost 20 years. And it's very nice of him to be in the middle of his other personal engagements to come here, run into 1 hour to talk to you about the cavity ring down spectroscopy. Rajkumar, yeah.
Thank you.
I'll give you this, just one more.
Good morning to all of you. Thank you, Professor Sundar for, I never call him Professor Sundar. First day he told me, don't call me Professor Sundar. I know him right from 1997. Okay, he used to come to our group meetings and participate. And I know him as a teacher than a colleague. Okay, he has been very instrumental in building my laboratory, and in any system you will have a lot of ups and downs. Whenever I was up, he was never there. Whenever I was down, he is always there to lift me up. He was there throughout my career so far, even today. Okay, so whenever Sundar asks me to give a talk, I cannot say no. That's it. Okay, fine. Thank you once again, Sundar, for this kind gesture, for giving me an opportunity to talk to MSc kids, right? You're all MSc. Okay. First time I'm giving a talk to MSc kids alone. Okay, good. Yeah. So, students, as he has already introduced me, it was an empty lab, not empty lab, actually the lab which was used before was given to me. And I have to start cleaning that with 25 kilograms of mercury all over. Okay, yeah, seriously. And cleaned and did all that and established. It was not an easy sailing for me. It was very tough because I am not like a synthetic chemist, where you need some glassware, some chemicals, and of course this, and some hands to work, and some departmental facilities. That would essentially start the journey. But in my case, I have to build right from the scratch, because you look at the title, cavity ring down spectroscopy and laser induced fluorescence spectroscopy. These two spectroscopic techniques. Techniques are known, but you need to build the facility. How do you build? It requires a lot of time, money, and it requires a lot of time, and it requires a lot of patience. And not only me, a student like you come there, and first year you will see, okay, we are doing some, sir, where is my paper? My student with some Professor X has published already 2 papers. So this is the pressure which builds on you. And it's not the fault of the student either. It's the fault of no one. But once we build this system, right, you can do wonders. That I know. To build this system, I took 12 years time. Okay, but 12 years I cannot keep quiet, keep a student, hey wait, you'll get a paper. No, I have to do something. Parallel, I was doing something, publishing papers, and I got promoted to associate, then professor, but not with my heart. But after that, that promotion is only a climbing a ladder. When you are born, day 1 you are day 1, and next day you are day 2, you grow up. So that happens parallelly. But how did I do? This is something I want to tell you. Okay, and I will explain you the facilities. While I am going, I will be very informal. I will be going through and I will be telling the stories in between, and please bear with me. Okay, so you can reach me. You can reach me at. Can you see this? Okay. Oh, if I point out here also, it will work. No. Okay, fine. It is working. So you can reach me at Rajakumar at IITM. You have my professional website, that is profrajakumar.com, okay, or you can go to the chemistry department. And so, although I have done shock tube chemistry, that is a high-end chemistry for the propellants and other stuff in aerospace, I have decided to come to atmospheric chemistry. Every day you cannot eat same idli sambar, right? Next day you want puri, next day you want masala dosa, right? Similarly, I want to do something different. So I started, okay. So let us get into the subject. So this laboratory has 2 wings. One is atmospheric processes, the other one is combustion processes. I do experiments and computational methods. Okay, this is it's like, you know, you cannot eat food only with one curry. Add something else. That is always good. That is your computational science. You do the experiment will tell you, show the observations. Computational, you can actually predict the observations, and you can compare how these 2 are, right? So that's why it is you can see experimental and computational is the foundation, and then I have built the structure. Okay, and now today we will talk about this. Okay, all of you are aware of troposphere, stratosphere, mesosphere, and all of you by evening you'll go to beach with your girl or boyfriends, whatever, right? So, and that's where we start the life here, right? You see that it goes in the troposphere and up to 10 kilometers, and the tropopause. Why this? See, if you look at the temperature, it is a negative scale and this is positive scale. So when you go up, it will be negative. All right, the temperature is negative. So when you go to Ooty, you will feel very cool, right? You wish to go there all the time, right? Sometimes it is possible and sometimes it is not, but make it possible all the time. So at 10, what happens is, see, this is a stagnation. That means a temperature, there is no change in the temperature for about 2 kilometers height. Therefore, it is a pause, like you are listening to music and you pause it. Decrease in the temperature is paused. And then, see, surprisingly, it increases, the temperature increases over the height. That is very interesting. Although it is negative, but still there is an, acclinement, right? So it increases. So when it is increasing, what is the reason? The reason is, in a simple terms, it is exothermic chemistry, what happens in the atmosphere. Lot of chemistry happens. It doesn't, you don't see, I can see you straight, you don't see something is between us, but lot of things are there in between us. So that is what, you don't see anything, but we see using the spectroscopic techniques, okay. We will focus on this troposphere and stratosphere, and then, and if you look at the composition of the chemical composition of the earth, we will not go into the details of the things, but for a simple thing, nitrogen is plenty, you know that, and oxygen is next, and the other one is argon. This red one, you see that, this carbon dioxide. If you look at the parts per in parts per million and parts per trillion, when you see this parts per million, it's methane is plenty. All the CFCs fall under this. They are actually parts per trillion, parts per million, parts per billion. But CFC concentrations of chlorofluorocarbon, concentrations are pretty low. But the nasty thing that the devastation that they have done is vast, right? Very huge. That's what you say. You know, it is not that all good boys are good girls in the class, but one nasty guy is good enough to spoil the entire classroom, right? Yeah. So I was like that. So okay. So okay. So right. So methane is something you need to worry about it, and CFCs is something you need to worry about it. I just you know, keep going with this. These are all self-explanatory. And if you look at the trace component I have shown you, see what are those? Rusty cycle, like you see this CFCs are 1 into 10 to the minus 7 percentage. Very, very, very tiny. 10 to the minus 7, you take 10 lakh molecules, one molecule will be there. But that guy is good enough to spoil all the 10 lakhs, right? A donkey which is eating quietly eats. The other donkey which is only, you know, making noise, it will go and spoil that guy also, okay? All 10 lakh donkeys are gone now, okay, right? So, if you look at the pollution, the kind of all the chemicals what you release, essentially they will contribute to the pollution. Look at Delhi. How many electrical poles you can count? I can see 6 or 7. Not beyond that. It's all haze. Look at, I don't know how people are living there. They must also be, you know, get accommodated with that. Okay, harmful chemicals. So we need to worry about these chemicals. We are the culprits. Okay, I'll show you the pictures why we are culprits. Look at this. During the lockdown, that was before lockdown, that was India Gate. And during the, look at how clean that is. Can you imagine? That is how it is. And before lockdown, from Chandigarh, I said Mohali, and from lockdown, start of the lockdown, you can see Himalayas. And after 1 month of the lockdown, you see that? You can see the snow. So, who are the culprits? I want, guys, you have bike, no? Right? So, you know how much uncombusted petrol you exhaust when you do that. When you see girl, no? What you do? Rise for no reason. Huh? And when the girl is sitting, that's even worse. Okay. So, it is all pollution. We do all this stuff, okay? That is same truth there also, okay? Okay, fine. Now, daytime chemistry is like OH and HO2. Sorry, this is these two, HO2, right? Not H2O. Please understand, this is a radical and this is radical. These two govern the chemistry, okay? These two govern the chemistry. Hydroxyl radicals, there is no board here, but yeah, I know interactive this one is, it doesn't matter. H2O is there, right? And ozone. Ozone, when it dissociates, it forms O2 plus oxygen. You are all chemistry graduates, you understand this. Oxygen in D singlet, singlet D state. That guy reacts with water and it produces 2 hydroxyl radicals. So, plenty of hydroxyl radicals there. You understand? And these hydroxyl radicals are like detergent of the atmosphere. That guy, methane is there, CH4. OH go and react with one of the hydrogen and takes off water, and the methyl radical is left. Similar, it does with every molecule, it doesn't care. It's a very universal acceptor, right? It interacts with everything, it falls in love with every molecule, okay? Now it leaves the radicals, but those radicals are radical by means, it's a, you know, radical students union, there is a RSU. Why that name is given? Because they are radicals, they are highly reactive, right? They are spontaneous, like you do something, they will all come like a mob. So, these radicals are highly reactive, we should understand that, okay. And next one is nighttime chemistry, it is all concentrated around NOx, NO3 and NO2, N2O5 and all this stuff, okay. The acidic rains are usually formed during the night time. Daytime, it is only water, okay, yeah. So, and if you look at aerosol, aerosol is a particle which is a conglomeration of few molecules, right? And a particle is there and water is accumulated over there, and the chemistry inside the aerosol is heterogeneous. It's highly heterogeneous, okay. Lot of people are working on this, and this is the next level chemistry that we have to do now. So far what we have discussed is, we talked about hydroxyl radical chemistry, and chemistry is, I mean, people are worried about that because composition of the Earth's atmosphere is based on that. So, but now people are coming up saying that no, it's not just homogeneous, heterogeneous chemistry also is very equally important. Of course, your ozone loss was explained based on heterogeneous chemistry, right? Polar stratospheric clouds, and you know the cycle, Molina and all, they got Nobel Prize because the chemistry that happens on the surface of the ice pellets, polar stratospheric clouds. If you don't know, probably I have the slide, I will see. Okay, now you see, what is this? If the molecule lives longer, suppose this 100 years CFC lives, it would have passed a path length of about 10,000 kilometers. That guy is joblessly, tirelessly walking in the atmosphere, 100 years, 643 years is free and 12. That guy can never be dead. He's immortal, right? And you have released such kind of compounds. Look at the plight of your atmosphere. Very sad. All of us released, right? So we are the ones who did all the damage to the atmosphere. Okay, let us not worry about this. And then if you look at this plot tells you everything. This red one is free on 12, right? If you look at this, how many, what is that? 425 thousands of metric tons were released, and there was a dip, again they started, but from 1995 it stopped, complete declinement. No one can use these compounds. We have found the alternatives, but in Velachery you get cages and cages. Yeah. When I asked for something, some guy said, sir, free and roll na kudukala sir, paravailla sir. Evlo sir venu ungalku oru ton venuma sir keta. Namaskaram. Okay, fine. Okay, now let us get into chemistry. So we are all playing, boys and girls and all, nicely playing because ozone is protecting us. You see that? Ozone is concentrated at what distance? 25 kilometers, right? This is concentrated from the seashore where you had nice time. That's what I told you, right? So, and once this ozone layer is tampered, you remember, you have kept on releasing the compounds, right? What will happen? This ozone is eaten away. It's not a big hole. Please don't mistake that. Concentration of ozone in that region is very less. That's all it is. Okay? When you take the globe like this and see from the bottom, that is the southern hemisphere, what you find is the concentration of ozone is reduced. That's what you call it as ozone hole, right? Yeah. And now come to the chemistry part. Now we are releasing all these compounds in the atmosphere, right? We know. And what is happening? Hydroxyl radicals are there. So chemistry is initiated with the sunlight. And nitrates are there. Sun sleeps, but chemistry is on. Okay. All these things, if you look at this O3, NO2, NO3, OH, O triplet P, chlorine in doublet P, oxygen in singlet D, these are all highly reactive species in the atmosphere. So, suppose if you want to ask me, sir, how long this compound will survive? You are saying Freon is surviving 643 years. What is the rationale for that? That is, the rate at which it reacts with OH determines that. Okay? The rate at which it reacts with OH. So, we need to actually measure the rate of the reactions. So, this is the chemistry part comes into picture. I slowly try to, there is a lot to describe, but given the 50 to 55 minutes of time, I would focus on how we measure the rate constants, right? And this is all the story behind the experimentation. Now you see why this chemistry is important in one simple slide. We'll explain. Look at this. This is a viewers. Sorry. Yeah. You have to cut this. Okay. Yeah. Otherwise, the teacher is dancing. So. Okay. Now, if you look at this VOC, volatile organic compound, it reacts with OH, NO3, O3 and R light, doesn't matter, it produces R dot. And by the way, if you take methane, you shine the light, one of the hydrogen can be easily detached, still CH3 forms, these radical forms. So, there are two ways the methyl radical can form. Always, chemically you can form the radicals or photochemically you can form. Okay, that's why I said this is the reaction with OH, NO3, O3 or photon. Okay, very good. And this guy is very reactive. Like, who is the nuttiest boy here? Huh? Nobody declares. I am. Okay. So, it reacts with O2 and forms peroxy radical, and it forms peroxynitrite, or it forms HO2 instead of NO2, it forms all these compounds, and it forms, it exerts RONO2 and forms RO, methoxy radical or alkoxy radical, and a phenoxy radical, whatever it is, right, depends on the moiety. And then it reacts with NO2 and it forms O triplet P and NO, and it reacts with O2 and form O3. Essentially, if you release a compound into the atmosphere, most of the times what you get is ozone. Well, it forms ozone in stratosphere is very good, well and good, but unfortunate thing is forms in the troposphere, right. So, tropospheric ozone is very nasty because it can cause the skin cancer, blood cancer, lungs cancer, what not, all cancers, huh? And Apollo hospital will earn money. Okay. So, sorry, this you have to cut. No, not Apollo, any hospital. Why Pratap Reddy will be angry with me? Okay. So when you go, so you need to understand these reactions very well. So, how one can measure the, see now I told you, one is photochemistry, right? One is this guy. Hey, I don't like this, you have a ordinary pointer. Okay. This guy is there, right? Photochemistry. It forms the radicals. So, you have to measure both photochemistry means absorption or emission. So, these two techniques I will explain today. With absorption, how do you measure the kinetics? With emission, how do you measure the kinetics? Let us see, okay. Now, how one can measure the absorption cross section? Because you need to measure the kinetics, you need absorption cross section. That is molar extinction coefficient. What is Beer-Lambert's law? A is equal to epsilon LC. Epsilon is a property of the molecule, right? Your DNA cannot be tuned. Don't try it, huh? You will go mad. So, epsilon is fixed and concentration you can play. Based on the concentration, path length and epsilon, your absorption changes, right? So, you measure the absorption cross section first. How do you do it? Very interesting. You look at this. These guys, it looks very simple, huh? I'll show you. Two reflective, highly reflective mirrors, 99.99, 99.99, 999, doesn't matter. You shine a laser beam, 99.99% light goes back, 0.001% goes in, and this guy is equally bad. It kicks out on 99%, 99.99% as a 0.001% and leaks out only 0.001% of 0.001% of the total intensity. Then you put a detector that I will explain you and measure. This is red without any absorption, but we are chemists now, we dump something. Then you measure, that is the blue line. So, what it does is, it is before the light dies naturally, see the light is trapped here, right, it will go back, go in, what is that, to and fro, it will be rotated, it is not so far, so slow, you can't see that, right, the velocity of light is 3 into 10 to the 10 centimeters per second, right, roughly. So, in that case, it will establish a resonance cavity. Light goes, it builds up the cavity. By the time, every hit it leaks out some light. So, you capture that. By the time it loses its intensity by 1 over E, that is a natural lifetime. After that, no photon exists. It would have passed the path length close to 100 kilometers. Take UV visual spectrometer, all of you have done UV visual spectroscopy, right, 1 centimeter path length. Here 100 kilometers I give you. I explained you very simple, right? It took 12 years for me. Huh? Yes. Now, I have made the animation, okay? You see this. This guy goes, kicks that, go in, goes out, but it goes back. Every time he did see, every time the photon leaks, now we record it. That's it. Now you dump, you fit the data. Now it is simple Beer-Lambert's law, nothing else. And I put some compound in that. Then this is tau. Tau 0 is the ring down time constant of, tau 0 is the ring down time constant without any compound, and tau is the ring down time constant with the concentration, with the compound that you have put it, right. So, the PMT is nothing but is photomultiplier tube. Every photon it hits, it will capture, it will count what is the intensity. That's what it is plotted there. Intensity of the light versus time. Okay? This is a simple principle in cavity ring down spectroscopy. Now you see, Beer-Lambert's law you take. Absorbance versus concentration. So what is that? It is supposed to, you increase the concentration to very, very high concentration, but still it is linear. Is it possible? What will happen? It will deviate, a plateau, right? Okay, he is very smart guy. He knows where to cut. Okay, now I am a good cricket player, by the way. So that's why I missed the catch. So when you plot this absorbance versus concentration, it's straight line, right? So but here epsilon you cannot change. L is the only thing which you can change. So when you increase the concentration, what will happen? See, that's what you see. So the measurements in the region where this is realistic, the measurements in this region are absurd, right? They don't have any meaning because this detector is saturated. You can't actually detect what it is, right? So in this region, that means concentration. Now you have to reduce the concentration for it. How much you can reduce? You can reduce to parts per million, parts per billion, parts per trillion. Still my Beer-Lambert's law I can see because my path length is 10 to the power of 6 times 1 centimeter. That means you can ask me, sir, why are you struggling to reduce the concentration, increase the path length? Yes, because the concentration of the species, the chemical compounds that you release into the atmosphere, they fall in the region of parts per million, parts per billion, sometimes parts per trillion. So for that you need to have a super sensitive spectroscopic technique, which is nothing but your path length you increase, enhance. That's what we have done. Okay. Now is it clear? A minimum of 50 kilometers path length is guaranteed. Very high sensitivity. PPB level detection is so trivial. Okay, I don't care. You give me PPB, okay, my spectrometer is there to detect. You see that? Nice, no? Yeah. See that? This is what is the design. Don't worry about all that. This is a mirror. This is another mirror. You can tune, these are bellows. You can tune. See, the angle between both of them is 0. A micron difference will take you to several kilometers of off. Micron difference, not much. 1 micron angle will offset because the reflection goes in this direction, right? So most of the times we spend time on. That's why we have tuned this with what is that, acousto-modulator. That's an electronic device. So the minute the mirror is going little bit off, it will kick it back. So it will make sure that the path length is always intact. Okay. So this is very super sensitive, right? Yeah. And then there is a power meter you can measure. This is a where is that? This is a dye laser pumped with Nd:YAG laser, and that is the probe laser, right? And this is an excimer laser which we produce the radicals here. How do you produce? No, hydroxyl radicals. How do you produce? Photolyze ozone. You pump in ozone, it produces O singlet D, and put in a lot of water, it makes hydroxyl radicals. So now you put your chemicals there. Now you measure the kinetics. How do you measure the kinetics? It's very interesting. You see, you are producing the radical here and you are probing. You are seeing how much is there. You produce the radical here, you ask the probe laser to go and probe. Probe means what? It absorbs. At the same time, maximum. Because most of the radicals are there, 100%. You probe it little off, 100 microseconds later. The concentration comes down because the radicals would have reacted with my reactant. 200 microseconds, 300 microseconds, 400 microseconds, keep on doing it. What is this? You found time versus concentration, time versus intensity. What you are measuring is intensity. Because you are giving more time, the radicals absorb. Right, so the light is reduced. So what is kinetics? Rate of change of concentration with respect to time. This is concentration with time, time versus concentration. It is, what is concentration here? Concentration is your intensity, because you are measuring indirectly. You cannot measure concentration there. You measure the absorbance and with respect to time. So this is what is kinetics, right? Exactly what we do doing the kinetics. But here we need to measure the absorbance. So you measure the absorbance exactly at the point where you measure. So there is no delay between these two. So how do we operate these two lasers? You ask this laser, there is something called, there is a delay generator. These two are joined. Oscilloscope, ozonizer, mixing chamber. Well, these two are not connected. Okay, leave it. So there will be a delay generator which talks to this laser. Hey, you fire now, and this guy will fire the laser, produce the radicals. Immediately, I will ask this laser also fire. I can ask this laser to fire whenever I want. See that? Now you can do the kinetics and absorption. So beautifully can be done. Okay, and all others you don't worry. We have written the software to acquire the data. By the way, this is not commercially available. Huh? You have to make it. You have to write the software to acquire the data. You have to talk to the equipment. I cannot talk to you which language you talk Marathi. I don't know. See what I am saying? But I know you are a human. You have certain properties. I get the properties and connect to a computer. The computer fellow will talk to you. Right? So nicely you can get the data from all the equipment. Right? It is all students like you have done from rural areas. Yeah. I am here because of my students. I have graduated 17 students with all this. So far, yesterday, day before yesterday, one got graduated. He is going to France. Okay, so now, this is the one. Look at this. Huh? I am very proud to show this. Huh? Seriously. This is all our own design. That is our own design. See, cooking food is a trivial thing, but who cooks matters. Amma cooks, it will be so tasty. You go and cook. Sister cooks also is fine. Little training is there. These days sisters are also not cooking, that's a different thing. Huh? Correct, no? But see, who cooks differs. So, hey, I listened, I heard, you cut this. Okay. Okay. So, not fair. So, it is all done by people who do not know cooking at all. They cooked all this. That's what I am trying to say. See? Looks so elegant, right? Yeah, fine. So, another one. Now, this was the previous case. This is something different. This is like this. Here, path length is only, the interaction is only this much. Here, the interaction is here to here. Where the absorption is weak, we use this. So, it overlaps longer time. You understand? It's not rocket science. Am I explaining in a tough way? No, right? You understand my English? Yes, sir. Good. Okay. So, I hope I am not talking like Balram Naidu. So, you know that character, right? So, okay. So, the thing is, now you see this. This is a YAG laser with, which is pumping dye laser. This is an XMR laser. These two are connected with a delay generator. So, I have a control on both the lasers. These delays are 100 microsecond delays. It will tell, hey, you fire now with after 2 microseconds. Look at that. This is a sophistication. It's a passion in that, right? Yeah. So, this is another one. My student has, this is called collinear photolysis cavity ring mass spectrometer. Right. I need to watch the time. This is what it is. It looks simple, right? You will see next picture. You see this? This is the one which is overlapping here. This much overlap. From where? From here to here. Yes. Longer line. Rest is same. Okay. Fine, guys. Now, this is all okay. Now you see. See, HCO radical, for example, formaldehyde you take, HCOH, remove that guy. One of the H is gone. HCO radical. Look at the absorbance, 613.8 to 615.8. 2 nanometers. Just 2 nanometers. Right. Resolution is 0.0001 nanometers. That means I can differentiate these two peaks because they are differed by 0.00, 0.02 nanometers, something like that. That means what is resolution? I should be able to see two lines which are separated by 0.0001 nanometers as two lines. If my resolution is 0.01, then I cannot see these two lines as two lines but as one line. Because my resolution is not good. It's like spectacles. It's like fan is rotating. You close your lids very fast, you can actually write your name and your girlfriend's name and you can see both the names. Okay? Correct? But if you cannot close and open, both are gone. Yeah. Okay? So be careful. When you write the names, you should be able to see that. And it is true for them also. Okay. So I have actually, this is done by John Fly and my student Srinivasulu has done this. You see this? How nicely it is matching. I said, okay, litmus test is over, don't worry. How did we produce HC1 is a big mess, I tell you. Gas phase chemistry. You have to do a lot of chemistry there. Okay? Let's not get into that. Now you see this. IO and methyl alcohol and IO and ETOH. Ethyl alcohol we have done. IO radical. Why iodine is important? Iodine is important in the atmosphere. Chlorine is important. ClO. Iodine is equally important. Okay? So we have done it. The temperature, all these things are given. Now you see, don't look into why did I all that, you leave it. Forget about why did I do methanol, ethanol, all that. Okay, now you see. See the kinetics what we have done, kinetics of IO with methanol. Look at, I told you, this is a laser, you produce the IO radical and in presence of methyl alcohol. You see, hey, you go and fire and probe the IO concentration. You probe here, probe here, probe here, probe here, probe here, give the time. How much time did I give you? It is 1 millisecond from 100 microseconds to 1 millisecond timer. And I have changed the concentration of my reactant methanol. This is the lowest concentration, second highest, third highest, fourth highest, fifth highest and sixth highest. When you increase the concentration, naturally the reaction should go forward. And that's what we have done. See the kinetics. Nicely it is done, right? And then you fit the data. And this is at one temperature. Let us say 298, this red one. You fit the data, how many data points should be there? 6. 1, 2, 3, 4, 5, 6. Like that we have changed, we have done the experiment with 6 temperatures. By the way, I have explained in 1 minute or less than 1 minute. My students struggled for 2 years to get this data. After establishing the facility. See that? See, I am telling you the happy part and the sad part also. Right? You want to get something, you have to work hard, man. You know what I mean? Okay? Nothing comes for free. First love thermodynamics. You want Aishwarya Rai, she cannot become your girlfriend. You have to really work hard. Aishwarya Rai is my timer. Okay. Fine. You see, boys are very active now when you talk about this. Girls are very upset I am not telling the examples. I will tell you, don't worry. Okay. So, now you see, with all the temperatures, this is what it is. So, kinetics are there. So, my students when they come now, they will try to control their laugh because they are discussing, I will be cracking this and they don't feel like laughing but they cannot control. You know, this is a problem always. Okay. Now you see. Computational I said no, desert. How do you do? Same thing, methyl alcohol you see, we have produced and IO radical, it abstract hydrogen. So, now you do the kinetic measurements. You know transition state theory? That guy goes up and jumps. One of the vibrations, loose vibrations become the translational. You remember that? Something is flashing, Apply oil to your hair, it will work. Okay. So, what it is? Kt is equal to kBt by h nu, h into q double dagger by qa qb into e power of minus e0 by rt. You remember that equation? No, I know, you forgot. Claisen mechanism you remember, orbital condensation you remember, but not kinetics. Every reaction goes through this kinetic theory, man. Transition state theory, you learned that. Orbital condensation cannot go just like that. Cannizzaro reaction cannot go just like that. All follow this fellow. First you read physical chemistry. Okay. Organic, you cook up something, add 2 chemicals and put the fire. Adupula pota, chemical ready aipoyadu. Adikapro you take, what is that IR? Everything, finally NMR. You know what is NMR? No more research. After that. That is organic chemistry. Hey, you have to cut this. Okay, fine. Okay, now you see. This contribution of this guy is very, TS2, where is this guy? So it takes from here, is very high. And the contribution of the other guy, TS1 is very low. So, computationally, this is a problem. Experiment will only see the molecule. It doesn't see this hydrogen, that hydrogen. But computational fellow, no, is the theoretical fellows. They look into, like, you know, they'll try to find out, what is that? Feathers on the boiled egg. That's what it is doing. It finds out which hydrogen is contributing maximum to the reaction. See? And I'll tell you the overall reaction. But this guy tells me, this guy only reacts, all other useless. Actually, computational chemistry is a wonderful tool. Right? So, my students are trained both in experiments and computational chemistry. I told them, in the event of you don't have anything, you are put in the forest, do research on leaves and publish papers. Seriously. I did that. 12 years, what did I do? I was doing only computation. I was known as computational chemist in this country. Unfortunately, I never wanted to get that tag. But now I am an experimentalist. I am happy. I struggled, I worked for 12 years, okay? Okay. Now this is ethyl alcohol. Same story. Molecule changed. Right? And there is nothing to teach about. All the concentrations. Don't get into those details. When you do research, you worry about it. The essence you need to understand is this one. Okay? Fine. Now, this is ethyl alcohol. All this kinetics drama I have done. All the transition states. How many? 1, 2, 3, 4, 5, 6. All 6 transition states. Probably 5 transition states I have found. Excuse me. Look at this. So, these two, TS2 probably, TS2, this is the lowest energy transition state. This is the TST essentially what we are seeing, right? And don't ask me why this is negative and all those details you get into later. When 2 highly reactive species are reacting, when the activation energy is negative, they fall in love and form a pre-reactive complex. They form a complex and they release the energy in this process, and from here to there they have to climb using this energy. That is the transition state. This is the transition, this is not. Okay. So, we have compared these experimental and computational studies, right? Now, well, this is IO with the ETOH and MEOH. You see that? Here, experimental, we have changed the pressure, and laser planes also we have changed. See, when you are measuring, you cannot say, I have measured, so be it, this is my number. Hell with you. No, you have to do all litmus tests. Is it getting influenced with the pressure? Is it getting influenced with something else? All that, okay? Now, these are all the kinetic parameters. You don't worry about it. Now you look at this. See guys, the difference is so beautiful. This is methyl alcohol, this is negative temperature dependence, and this is ethyl alcohol, this is positive temperature dependence. Just by introducing CH2 group between OH and CH3, see the chemistry, how different it is. So it all matters who comes in between 2 of you. That guy spoils the whole thing. Look at this guy, CH2. You know what I am saying, right? That they understand very well. So similarly, CH2, see, this methyl alcohol is very nice. See, we have done the same experimental, used the same experimental facility. Both theory and computational we have done it. Right? You should understand the groups, the minute you add on the moieties, make the compound lengthy, chemistry becomes complicated. Okay? Did you learn something? Yes, sir. Sure, I'll ask you questions now. Now, what should not come between 2? CH2 should not come. This guy is thinking something different. I know this guy. Okay? Yeah. Okay, forget about Craig. All this I'll skip. All this cut, okay? Because I need to show something else. Okay, so this is another experimental setup. I thought I will go through all this, but not required. One example is good enough. Guys, I told you absorption, right? What about emission? You know, you might have seen somebody drinking too much, right? Okay. After some time, he will come out. Energy goes out, right? So, you excite the molecule with high energy instantaneously, that guy goes crazy because full of energy. He can't tolerate, he will be doing like this and then he will fluoresce and he will phosphorus. See that. Now, you have done the measurement using absorption method. Now, we will do the measurement using emission method. Not all radical emits, not all radical absorbs. So, the radicals who absorbs, we measure this kinetics using cavity ring noise spectrometer. And the radicals who emits the light, we measure using emission. See? Understand, no? That's it. Simple. Yeah, I am a good teacher, by the way. Yeah, you don't believe. Okay, now, okay, see, he is laughing. So, now, hydroxyl radical, ground electronic state, upper electronic state, you know that, right? Suppose you want to vibrationally populate, put a stove, that guy will go in the ground electronic state, maybe it will go a little bit. Hot bands, you know that hot bands, right? V equals to 1 to 0, 2 to 1, they are hot bands, or 1 to 2, all are allowed? Then well, go through that, I read long back. Now, but if I want to see the electronic absorption, you cannot put a stove, temperature alone will not do, you need a instant energy, put a laser, that guy goes up and emits the radiation. This is ground electronic state and this is upper electronic state. V equals to 0, V equals to 1, V equals to 0, V equals to 1. This is not to the scale because it's a lot of energy, right? Now, you see that? I excited 282 nanometers. This is hydroxyl radical. 282 radical I produce using a YAG pump dye laser and double it and all that. That is my headache I produce. This guy is gone to V equals to 0 to V equals to 1, allowed transition. And now that guy will come from 1 to 1 at 308 at lower energy. Rest is gone. Where it is gone? Heat. Very good. Photochemistry, not this chemistry. Huh? Okay. Now there is also photochemistry, by the way. So 1 to 1 is allowed. Now another process is 1 to 0. What is that? Intersystem crossing, right? Then it is a non-radiative transfer, heat energy. And this guy comes down 0 to 0, which is allowed 308. So I am exciting at 282 and observe the emission at 308. That means I should have the equipment with well equipped with only I should detect 308, nothing else. How do I produce? Using 248 nanometers. I produce radicals using 248 nanometers, excimer laser. I excite at 282 nanometers, see the emission at 308. So I should have 308 band pass filter, which allows only 308. Otherwise, all of them will come into photomultiplier tube. This guy absorbs everything, no. PMT is, it doesn't care. Hey, you can't, hey, you observe this guy to leave that. No, I cannot do that. Put a filter. Okay, that's what it is. Using this principle, this is photomultiplier. By the way, this cell we have made it, nobody could do it in India. Simple cell, 6 ports, 1, 2, 3, 4 and 5, 6. I went to US, sat with the glass blower, I know glass blowing. Okay, designed and carried with me in the carry-on. I was caught in the customs. What is this? I said, I explained, Baba, I am a professor. Unfortunately, nothing is available. You have to buy and yeah, this is a 25,000 rupees invoice it is. And I said, okay, go. You're a professor, beggar. So he left. Because I am bringing, no, I am getting something which is not authorized. So 2 cells I brought like that, okay? Because once it is broke, nobody can do it. So this cell, what this is a photomultiplier, this is a photomultiplier tube, bottom we have blocked it. And we can produce a thermocouple, introduce a thermocouple and measure the temperature here before the experiment, after the experiment and remove it. Okay, and this is the 248 nanometers to produce the hydroxyl radicals. I explained to you in the beginning, right? And 282 nanometers is another laser which goes from this side. And PMD is sitting there. And there is a band pass filter here, some PMD, in the picture it is down, but it is up actually. Band pass filter, it attracts only 308 and it doesn't catch 248, it doesn't catch 282. So now, I produce the radical, principle is same. Produce the radical using 248 nanometers, this is XMR laser, and I am talking to these two with a delay generator here, right? And once I am talking to these two with a delay generator, I produce the radical here and I will ask this laser to fire after at 0 time, 100 microsecond, 200, I am just giving a glimpse. You can measure it at 10 microseconds also, depends on the reaction. And go up to 1 millisecond, maybe 10 milliseconds, 100 milliseconds you go if the reaction is very slow, okay. So this is the cell. Essentially, I have only shown the shell, I have not shown the actual complete setup, okay. Yeah. And now you see this, some molecule we have taken, delay is up to 1.2 milliseconds here. Here how many have done? Without very low concentration, 8 concentrations I have done for 1 temperature. If you fit the data, you will see 8 points, and how many temperatures have 1, 2, 3, 4, 5, 6. So why this temperature range? You need to do the reactions in the temperature range that is relevant to the atmosphere, Earth's atmosphere. So you range from 320, we never go, and lower side is 240, okay. We never go that side also, okay. But entire range we try to measure, okay. And now this is the complete setup. You see this? We have established this facility, and you can see this is the collimating lens system, and there is a band pass filter, photometric. By the way, this also took, actually this took longer time than CRD. I could not get the LAF signal. It took 15 years right from beginning. My student Avinash, he never left, he is in Finland now. After his PhD he got the signal. He has done PhD with CRD and other stuff, but he has done this. Really, passion should be there. You should be highly motivated to come forward to do research. Well, you go and learn Python, what is that? Python is the latest language, Java, HD and all that. You measure and you become keyboard operator, you live. I am not undermining them, but passion, you live with passion, this is what it is, okay, fine. This molecule Avinash has done, Avinash Kumar, see that? And when he has measured, I have shown you already. So you can do the kinetics, and similarly he has done the computational, I am sure. All the transition states we have found, because you see how many, 10, all the transition states he has found. And we found which one is maximum contributor. TS6 is maximum contributor, this guy, okay. So computationally you go into the details, experimentally measure, okay. And now you can compare the kinetics with theory and experiment. And once you have this is a second order rate constant. What are the units? Concentration, inverse, time inverse. So you multiply with the concentration of hydroxyl radical. What is left? Second inverse. 1 by that is seconds. That long the compound survive in the atmosphere. The rate coefficient what you should use is at room temperature. Or suppose you are measuring the lifetime at 0 Kelvin. You go and measure, get the rate constant and measure at that, calculate at that temperature. So it gives you spectrum, complete spectrum of atmospheric lifetime. Then you average, that's called diurnally averaged lifetime of the molecule, okay. Okay. So I will skip this relative rate measurement because it is something like I want to measure the reactivity of A with OH, and what I do in case if I don't have LAF, I don't have CRD, this is the first experimental setup. What I have done, put B also with OH. B and OH kinetics are known, already reported. A and OH kinetics are not known. So measure the loss of A with respect to B. Take the ratio of the concentrations, take the ratio of the rate constants. Unknown rate constant you can calculate. But unfortunate thing is you have to depend on B plus OH kinetics, somebody has done it. That is the disadvantage. If they are erroneous, the rate coefficient what I am measuring and reporting also erroneous. But the advantage is it is a static cell. I can take the sample and analyze in the mass spectrometer, take the complete spectrum of the products, and now I can say with this reaction in the atmosphere these many compounds are formed. That is the advantage. So always every system has pros and cons, right? So we have done it. This is I have explained in a simple way. Okay. This is the molecule I have taken. I want to show you. You see mass spectrometer when you I think Ramya's paper this is. This methyl propionate, if you take these many compounds are there, and I am sure next also GCIR we have done, and you could record all the IR spectra of all the compounds. So compound concentrations are microns, like very very low concentration ppm, but still we have super sensitive spectrometers and we can. So what essentially towards the end of the day I can say is, you give me a molecule, I can tell you the fate of the molecule in the atmosphere. How long it will survive, what are the compounds it can produce, how much global warming it can produce, how much ozone it can produce, how much ozone it can eat, everything we can say. That is the whole story. Okay, this is the mechanism. Once you know the compounds what are formed, you can propose a mechanism, how the reaction are. That's all it is. This is the lab. One side of the lab. I have another side too. Okay, take home message is the complete fate of the compound in the atmosphere can be, yes, in our laboratory. If you are coming, let me know in advance so that today is Sunday. I will ask my student, one of the student to be there, they will show you, take you to the lab. It's a really beautiful, best lab in the country, probably one of the best labs in the world. I am very, very, proud to say this. We have done this because of the students like you. Okay? Thank you very much.